In the last class, we were discussing about the transistor phase shift oscillator. I have given the circuit of the transistor phase shift oscillator and explained its operation. And now I shall give the expressions for the frequency of operation and the condition on the parameters of the amplifier, namely the HFE or in the RE equivalent model, the beta AC of the transistor. We have seen that the circuit is a transistorized circuit, and the amplifier is a fixed is a self-bias circuit as shown here. Let us consider an amplifier of this type with a collector resistance R1 and R2. In fact, this is the circuit we were considering, and here is the output point, and from here onwards the feedback is provided through a three-stage RC network. And as I mentioned, there are different kinds of phase shift networks that can be used, and one such network is as shown here. Please note that in this circuit, the last RC stage is changed to be a series RC stage, and in this circuit now, please note that the last RC stage includes the input impedance Ri of the amplifier, and then R dash and then C. Now, if this circuit is analyzed, we can arrive at an expression by applying the Barkhausen criterion. That is, a loop gain has should have a magnitude of unity and a phase of 180 degrees or 180 degrees plus a multiple of 360 degrees, since the amplifier itself contributes for 180 degrees of phase shift because of negative gain. Now, with that analysis, or by applying the Barkhausen criterion, we can find the frequency of operation as 1 by 2 pi RC into 1 by square root of 6 plus 4 RC by R. So naturally the gain depends on RC, and this is equal to 4 RC by R, and then there is a condition on the gain of the amplifier. In the hybrid parameter equivalent, the parameter HFE, the short circuit current gain parameter HFE, should be greater than 23 plus 29 R by RC plus 4 RC by R. So this is the expression for the HFE. So we find that for different R by RCs, the HFE requirement changes, and the optimum or the minimum HFE that is required turns to be around 44. So HFE should always be greater than 44, and in fact in a given circuit it should be greater than this figure for the transistor to be able to oscillate and provide you sustained oscillations. Please note that the final stage has an R which is equal to, as I mentioned earlier, R is equal to R dash plus Ri, and Ri is of the order of beta Re in the case of the RE model, and in the case of the hybrid model, this Ri is approximately equal to HIE. Now, for a given transistor amplifier, one can determine what is the frequency of operation, and one can also find out what is the HFE requirement for the transistor for the circuit to be able to oscillate. And the inverse problem, that is the design problem, also can be taken up, and one can determine the parameters R and C given the frequency of operation and given a particular HFE, a particular transistor with a given HFE. So, that is the design problem, which is inverse to the analysis problem. Now, the same phase shift oscillator with a FET circuit can be given as shown here. So, consider an amplifier, first consider an amplifier with field effect transistor and with the source resistance, this is the bypass capacitance for the source resistance, this is the drain resistance and VDD. A voltage divider network can be added here if you follow a voltage divider network for biasing purposes. Please note that this does not include that. So, the biasing is through a voltage drop across RS. Now, between the input and output, now apply the feedback. So, naturally you need a 3-stage RC circuit to provide a phase shift of 180 degrees, because in the case of the FET amplifier also you have a phase shift of 180 degrees offered by the amplifier itself, because the gain is negative. Here the last stage resistance is also equal to R, because the input impedance of a FET amplifier is almost infinity. For all practical purposes it is infinity. Hence, so the last stage also has a resistance of R. Now, we know that the expression for gain is equal to GM into RL, whereas GM is the transconductance into the load resistance, and load resistance includes RD as well as the feedback network, because the feedback network also loads it. Now, RD in parallel with the feedback network, without feedback the gain is GM-RL and RL includes only RD. But please note that the channel resistance, the drain to source channel resistance is also present. So, that resistance R small d also comes into picture, and in this particular case RL is equal to RD, the parallel combination of R capital RD and then small rd. So, this is the expression for the load and this is the expression for the gain. Now, the frequency of operation can be obtained from the expression which we have derived earlier. It is equal to 2.2 square root of 6 RC, because no RI is coming into picture here. So, this is the frequency of operation. This can be obtained by using the Barkhausen criterion. Any questions? Questions? Here also please note that the gain should be greater than about 29 for it to operate, for the circuit to work. there is a mistake here. This RC is outside the square root. Please make this correction. RC is outside the square root, and the gain should be greater than 29 for it to operate. This is what we got in the last class. For the circuit to operate, for A beta to be equal to 1 or for A to be slightly greater than 1 by beta, so A should be greater than 29, because beta of this kind of a network is equal to 1 by 29. Hence A should be greater than 29. And the frequency of operation is, expression for the frequency of operation is this. Now let us consider another interesting amplifier circuit. It's known as the Wien-Bridge Oscillator circuit. As the name indicates, so this oscillator circuit uses the Wien bridge for providing the feedback with the required phase shift. And the beauty of the circuit is that it offers highly stable oscillations. The frequency doesn't vary much with the supply variations and the temperature variations. So let us look at the circuit and discuss about it. So you consider an op-amp amplifier. Op-amp is a, as I mentioned earlier, is a difference amplifier with inverting and non-inverting inputs. And the input for the op-amp comes from a bridge circuit known as the Wien-Bridge circuit. It has a series RC in one branch, and it has a parallel RC in another branch of one side of the bridge circuit. On the other side of the bridge circuit, it has only resistances. Now apply the difference voltage in the bridge, difference voltage of the bridge to the input of the operational amplifier. So a bridge has an input between this terminal and the ground, and this is the bridge difference output, which is fed to the amplifier. Now from the amplifier's output, you drive the bridge. So this is the Wien-Bridge Oscillator circuit. And if we call it as Z1, impedance Z1 and impedance Z2, how much is beta here? If V0 is the applied voltage, out of V0, what fraction goes to the feedback circuit? If this is the feedback voltage, because that is the feedback voltage being applied to the input in the negative direction. Now this is the feedback voltage, that is output of the bridge, and this is the input of the bridge. Now what is the relationship between Vf and V0? So please note that going by the voltage divider network on this side and on this side, so this voltage, if you call this as B, terminal B, terminal D, and this one is A and this one is B, the voltage at B minus the voltage at D is equal to the feedback voltage. Feedback voltage is voltage at this point minus voltage at this point. That is the feedback voltage in the negative direction. Now, how much is VB in terms of V naught? VB is a voltage division between R4 and R3 from V naught. Therefore, this is equal to R4 by R3 plus R4 into V naught minus, so this is VD is a voltage division between Z2 and Z1 from V naught. So minus, so Z2 by Z1 plus Z2 into V naught is equal to the feedback voltage Vf. Therefore, in this circuit, what is beta? So beta is equal to Vf by V naught, and that is equal to R4 by R3 plus R4 minus Z2 by Z1 plus Z2. Yeah, there is a question there. Okay, sure. So this is beta. Now, what is the gain of an operational amplifier? For an ideal operational amplifier, the gain is infinity, and in practice the gain is of the order of a few tens of thousands. So there are different kinds of operational amplifiers giving different amounts of voltage gains, but please note that for all practical purposes this is very high. And for A beta to be 1 or slightly greater than 1, beta should be almost equal to 0 when A is very high. So beta should be a small quantity delta, so which is equal to 1 by A, the gain of the amplifier. Now this oscillator has here, please note that here the op amp has a gain of gain with 180 degrees phase shift, and now if this bridge offers another 180 degrees phase shift because of these two impedances Z2 by Z1 plus Z2, and Vf is equal to 1 by beta, which is very small, the circuit will oscillate. Therefore, at what frequency does the circuit oscillate actually? When beta is almost equal to 0, it oscillates. So beta is equal to 0 means it is at the null of the bridge the oscillator oscillates. So it is a bridge circuit, and at the null of the circuit the oscillator oscillates, and at the null the Barkhausen criterion, that is mod A beta is equal to 1, is valid, and the phase shift of 180 degrees is also valid because of this term. Now from this expression, if you equate these two impedances, and then find out an expression for the null condition, so you will find that the frequency of operation is equal to 1 by 2 pi RC, and there is another condition, that is R3 by R4 is equal to 2. So why is it so? So what we are saying is, the condition is that R3 by R4 is equal to 2. That means this is twice of this resistance. That means the feedback voltage is 1/3 of the full voltage. And at that point the null occurs. The null occurs at that point where this voltage is 1/3 of V naught. Why should that condition be placed? Please note that here there is a series RC circuit and here it is a parallel RC circuit. Naturally its impedance is lower than this one's impedance. And at the point where the phase shift condition is valid, so this impedance becomes twice of this impedance. Therefore, on that if you impose this condition that null should be occurring, so this resistance should be equal to twice of this resistance and this impedance is equal to twice of this impedance. So that means here Z1 is equal to twice of Z2 in magnitude. And in phase also it becomes equiphase but with opposite directions, with opposite signs. Now that is the condition for null, and therefore from this condition and this condition is arrived at, and these two are the conditions for the oscillator to oscillate. Rather, this is the condition for the oscillator to oscillate, and the frequency of operation is 1/2 pi RC. At 1/2 pi RC, please note that the resistance R and the impedance of C are equal. So there are two series impedances of equal value and it's a parallel combination of impedances of equal value. And the frequency of operation is this from that. And for the oscillations to occur, R3 by R4 should be slightly greater than 1, 2 plus some small delta. It is a small quantity. Now the question is it necessary that this R, C and this R and C are equal? It is not necessary that these R's and C's be equal. You can use R1 C1 here and you can use R2 C2 here, in which case the expression for the frequency of operation would be like this. In fact, first the condition for the frequency of operation for the oscillations to occur is like this: R3 by R4 should be equal to R1 by R2 plus C2 by C1 plus of course a small quantity delta. R3 by R4 should be larger than this, therefore R3 by R4 is equal to this plus a small quantity delta. And the frequency of operation is given by, or can be obtained as 2 pi into square root of R1 C1 and R2 C2. It becomes the geometrical mean of the time constant R1 C1 and the time constant R2 C2. And this is the Wien-Bridge oscillator, and the frequency stability can be achieved because of this null condition. This null condition is totally dependent on the ratios of the impedances. It does not depend on the voltage gain. If the voltage gain is large, so there is still the null condition is valid almost at the same point. So if the power supply increases, and as a result of the power supply, if the gain of the operational amplifier increases, the gain of the operational amplifier may increase, but still the condition for null remain the same on the ratios of these resistances and the impedances. Hence, the frequency of operation solely depends on the component values for all practical purposes.
So can it be used with OP amplifiers only?
There is a question there. The question is whether this Wien-Bridge oscillator circuit can be used with op amps only. Here, as far as the amplifier is concerned, we had only one condition placed on the amplifier, that it has high input impedance and the gain is very high. That's all. If that means if you have a multi-stage amplifier, transistor amplifier or a FET amplifier, so such amplifiers also can be used here. In fact, an op amp has a multi-stage transistor or FET amplifier inside it. Hence, the Wien-Bridge oscillator works with any amplifier with very high gain and high input impedance. Any other question?
So this we have been using impedance Z1 that is in series, and then again as a parallel. Anything special about that? Is there any advantage, or we can use anything?
The question is, we are using a series combination here and parallel combination here. Is there any speciality about it? Yes, obviously. The point here is we have 2 points here. One is to have a null, and at the null you should have 180 degrees of phase shift. And these two conditions can be met if you have this kind of arrangement. So please note that this is an impedance with some phase angle theta, and this is an impedance with phase angle minus theta at the frequency of 1 by 2 pi RC. Okay, if one offers a positive angle theta and the other one offers a negative angle theta. And because of this combination, you can see that, so this is equal to the phase shift can be 180 degrees at that point phase shift of this feedback network, and the null can also be achieved in the bridge circuit. So that's why these combinations are chosen here.
So the Z we write in this equation, do we need the mod values of the Z?
The Z we used in this equation, no, these are absolute values. These are absolute values, because it is just a voltage division between between Z1 and Z2 and supplied by V0. Therefore, there is no modulus here, and that is why we are getting an expression for phase shift here. In Z1 plus Z2, the imaginary terms get cancelled. That is the beauty.
So if we use R1C1 and R2C2, then it also cancels?
Yes, even for different combinations of R1, C1 and R2, C2 also it can be seen that at a different frequency it gets cancelled. And that frequency of operation is this, F0 is equal to 1 by 2 pi into square root of the geometric mean of R1, C1 and R2, C2. Now, let us consider a small problem. So, we shall take a resistance R3 in this circuit. Let us consider, let me write down here itself. Let us consider an R3 of 300 kilo ohms. So, this is 300 kilo ohms and R4 is 100 kilo ohms. And R1 is 51 and this is 1 nanofarad. 51 kilo ohms actually, and R2 is also 51 kilo ohms, and C2 is also 1 nanofarad. Now, with this combination, we can find the frequency of operation as F naught is equal to 1 by 2 pi into RC, which can be shown to be 3.1207 kilohertz. If you reduce R and C, the frequency can be increased. But please note that the operational amplifier should yield high impedance at that frequency. The condition on the operational amplifier, the conditions we placed on the operational amplifier are high input impedance and very high voltage gain. So, at the frequency of operation, this should be valid. If you want 1 megahertz as the frequency of operation, at 1 megahertz, the op amp should give you a very high input impedance and then high output impedance. So, let me mention here that the op amp 741, which is being used in your laboratory, offers a very high voltage gain at low frequencies. The voltage gain is of the order of 10 to the power of 4, but at 1 megahertz its voltage gain is unity. At 1 megahertz its voltage gain is unity, its gain bandwidth product is equal to unity. Therefore, at 1 megahertz it gives you a gain of unity. Now, can you use the op amp 741 in a Wien-Bridge circuit for oscillations at 1 megahertz? So, naturally you cannot use it. So, while selecting an op amp, we have to see that the op amp has very high gain at that frequency.
In this example,
Yes, it should be greater than 2. In this particular example, it is chosen as 3. In which case, beta is definitely larger than beta is a sufficiently high quantity. Still it oscillates. The only difficulty with high beta is that the null condition is not valid. It deviates from the null. The point at which A beta is equal to unity is valid, because here in this circuit, in this particular example where this is 300 kilo ohms and this is 100 kilo ohms, so this is 3 by 4 minus this quantity is equal to 1 by A. So, this beta is not 0, this beta is sufficiently high at which the oscillations occur. So, when beta is sufficiently high, that means it deviates from the null and the frequency stability is not that good, but it does oscillate. And for frequency stability to be very good, this should be equal to 200 kilo ohms, slightly more than 200 kilo ohms. The reason why I took this problem is that it's the problem given in the book, but I should give in the strict sense for this circuit to work as an operation as a Wien-Bridge oscillator, it is 200 kilo ohms plus delta. It should be. Any other question? Now, there are different other kinds of oscillator configurations possible, because for the feedback circuit you can use inductances also. Instead of RC circuit alone, you can use RLC circuits, and when RLC circuits are used, you have definitely a higher phase shift, but the inductors have the disadvantage of bulkiness. But the advantage with RLC, using RLC circuits, is that you can have very high frequency oscillations. You can have oscillators at megahertz, tens of megahertz range. And oscillators can be built to work in the gigahertz range also at microwave frequencies by using cavities, microwave cavities for the phase shift. So here I like to stop this topic, and if you have any questions, I like to answer them. Any questions?